Now in this chapter we are going to see the applications of differentiation. In the previous chapters we had seen the relationship between x and y. Always there was a y and x in a coordinate system. We were trying to draw the graph and make interpretation how derivative affects our function, or what does it say about the function. Here we are going to see the same thing but with different variables, how different variables in our real life are connected. For example, temperature and the time, the height of the tree and the time, they are connected. For example, we know that in the poles ice melts and we are concerned with the rate, at what rate the ice is melting. So with this type of in this first part where we'll be given the relation, it will be already given the relation. Based on the relation, we will try to find the rate of change at specific time or the average. And in the part B, we are going to construct the relation, and based on the relation, we are going to do the same thing like in here part A. So here from your book, I chose some relationship with the different variables, with the height and the time mostly, or the cost and the products. So let's see in the problems. I will solve 2 questions from your exercises, but in your book you also have some problems, so you need to check them, solve once. Here in a hot dry summer, water is evaporating, okay, from a desert oasis. The volume of water is remaining after T days is given in this form. The question is, find the first average rate of change. So imagine you have a relationship, and I know it's a parabola, but let's say we have some graph, and to find the average, what do I need? I need the beginning, and I need the 5th day. What will be the volume? Okay, I guess it's reversely, it's higher. So the idea is I need to find the initially and finally. So initially, okay, well, so initially the time 0, the volume is, what's the volume? It will be, if I put instead of T0, it will be 2 times 50 square. And after 5 days, the volume will be, if I put instead of T5, it will be 45, so 2 times 45 square. So initially it's the highest, then finally it's decreasing, so you can go let's do initial, final, and the average rate of change, the average rate no matter what. Okay, it's usually final minus initial, but you can go reversely, no problem. Okay, 2 times 45 square minus 2 times 50 square, and it will be initially, it will then 5 minus 0, the time, and it will be, if you calculate this one, 190 meter cube per day. So it's actually a negative result. You will get a negative result, but what does it mean? It's decreasing. The volume is decreasing. That negatively means that one. And in part B, they're asking instantaneous rate of change. When you see this instantaneous, it means about the differentiation at that time. So what do we need to do? We need to differentiate with respect to time, the volume. So it will be 2 times 50 minus T, 2 times 2. Okay, let's do it directly. We use the chain rule, times minus 1. So what will be the result if you minus 200 plus 40 plus 40? So at 5, so the derivative, the volume, okay, let me do it like this, at 5. So what do we do? Minus 200 times 4 times 5, it will be negative 180 meter cube per day. So the negativity, again, it means just decreasing. The negative sign, what you get from the meaning, is just decreasing. Okay, this is the rate of change. Well, let's see one more problem. Problem number 7, again about the water, I guess. Is it evaporating? Okay, with the rain, the water here in this case, we have a tank which contains this much of water. 8 fully drains at 80 minutes. So there is a relation is given. So the first question is find the differentiation of the volume with respect to time. So it will be 50,000. Okay, part A, let me do it here. 50,000 times 2, 1 minus t by 80, right, times minus 1 by 80. So this one is, okay, you can simplify just to indicate that this means it's a, what is it? It's a line. We had quadratic, its definition will be a line. So if we simplify the numbers, just to say, it will be 50,000 divided by 40, 5,000 divided by 4,000 divided by 4, if I just simplify it. So, oh, I forgot about the negativity again, minus 1, minus 1,250, 1 minus t by 80. So let's quickly draw this line. What will be? I just need the intercepts. It's a line. So when t equals to 0, it starts from negativity. Okay, it will be here. And when the volume is 0, when it fully goes out, what will be the time? It will be the volume and the time 80, right? At the time 80, so it will be just line. It's part A, and part B, they're asking at what time was the outward facet. The outward facet is always, from picture also can be seen, it's at time 0. Okay, and the C, find the second differentiation here. We just need to find the second derivative. It's always constant and positive. Show that we need to show it. Let's do it. It's just meaning take the derivative of the first derivative. Okay, if I take derivative of this one more time, what will be? Minus 1,250. Derivative of this one will be minus 1 by 80. Okay, so it will be division of these two, so 125 divided by 8. Can I simplify it more? No. Okay, let's leave it like this. So what does it mean? It's a constant, just a number without t, and it's positive. Yes, what does it mean? What does result tells us? The second derivative, if you remember, the rate of change is increasing. Okay, the first derivative tells about the rate of change, increasing or decreasing. If the second derivative is positive, the rate of change is increasing at a constant rate.